in this. Okay, I understand. So this is last seminar in this semester, and we have honor to hear Tomasz Smołka. In fact, I wanted to ask you, are you finishing your PhD?
Yes, I am finishing my PhD, and I actually try to find a postdoc. Yes, so
okay.
If someone knows something, please let me know if there is a good position.
So yes, I recommend Mr. Smołka. He's very responsible person, very talented. Okay, so please begin.
Okay, thank you very much. And I am a PhD student from Department of Mathematical Methods in Physics from local faculty. And this is a joint work with Professor Chruściel from Vienna. And so this is the last seminar. So I would like to thank very warmly to the organizers for the opportunity that I can present my result, and for their all hard work to prepare organize the seminars. Okay, my talk is devoted to Hamiltonian charges for three separately considered theories on de Sitter background. And I will start from Maxwell theory, and this would be the as a warm up. Next, I will talk about weak gravitational field, and that consumes most of my time. And here we have problems with convergence of charges, so we propose some renormalization procedure. I will discuss the energy in details, and in the end I will very briefly talk about scalar field theory. Okay, in each case the asymptotics is modeled on the evolution of the space-like Cauchy problem with smooth initial data. In the case of weak gravitational field, we use Friedrich's theorem to establish the expansions. I will talk about it in detail later. Okay, so we will use Bondi coordinates. Our background is roughly the de Sitter metric, which in Bondi coordinates looks like the equation 1. Alpha is related with cosmological constant, and we assume here that the lambda is greater than 0, but most of the formulas works also in the case of Minkowski and anti-de Sitter. There are of course the differences in topology, and you cannot exactly extrapolate the formulas, but a few some formulas works in also in de Sitter, but some not. Let's assume that we consider only the de Sitter spacetime. Okay, so as we know, in the case of de Sitter, we have cosmological horizon, and on cosmological horizon, the vector field, Killing vector field d over du change its nature from time-like and space-like. And maybe here is a best, I will roughly describe the physical situation. So we will consider the compact astrophysical system. Compact should be understood in a cosmological scales here. And we consider the world line of an isolated system, and such worldline is well described by a time-like geodesic in de Sitter spacetime. Such geodesics are orbits of a Killing vector fields. So at the moment we can call such a vector field by X, and that Killing vector field is time-like along the geodesics and tangent to it. Now we consider a light cone with a tip on that cosmological system, and we calculate the Hamiltonian charges of linearized theories, Maxwell, gravitational waves, and scalar field on such light cones in a de Sitter universes, in the de Sitter universe, and also the flux. Okay, so let me go to the first example. Okay, I should also mention about the Killing vector field. So the Killing vector field is the field which preserves the metric, and in the de Sitter spacetime we have that standard du temporal field, which is a Killing vector field. We have also rotation generators, and also another 6-dimensional spacetime, which in Minkowski spacetimes are translations and boost, but in the case of the de Sitter spacetime, they are not so easy. And here that Ri, Pi, and Li are just a constants, and Ni here depends on coordinates x, a on the sphere, and they are dipole functions on this unit sphere. Okay, next we go to the first theory. We will consider Maxwell field in vacuum. At the beginning, we consider field with source, and okay, the Lagrangian density is given by a standard formula 7 given here. Okay, so, and next we make the Legendre transformation, and a standard canonical momentum density is proportional to the Maxwell field and given by equation 8. But if we use the standard formula for Hamiltonian current, that is gauge dependent, so we fix it by introduce the different differential operator. I do not want to talk about it now. I only would like to say that if it acts on the potential vector for vector potential, it acts as equation 10, and using such formula we will receive the Hamiltonian current given by equation 11. Okay, so next we are interested in flux. So if we consider the Lie derivative of Hamiltonian current density, it is given in full generality by equation 12. So we have a term which is purely boundary integral, but it also contains terms proportional to the sources, and such terms which vanish if X is a Killing vector field of background. And I also would like to highlight that there are no assumptions about Y. So if we would like to have a general, so we would like to have a flux, so the derivative of Hamiltonian as a boundary term. We only need to have assumptions about sourceless field, and that the Hamiltonian field is a Killing vector field. And okay, we are interested in good asymptotics, so we consider only conformally smooth Maxwell fields here. Hello? Okay, I will continue. And such conformally smooth Maxwell fields has the expansion of FAR, that AR angular coordinates are given by 13. And if we here assume the sourceless field, all other asymptotics can be recovered from Maxwell, vacuum Maxwell equation.
Excuse me, in this equation 13, these dots means that it goes like our next term is what?
Yeah, okay, yes, a good question. Thank you for that. The next, so only minus integer are here, so we do not have logarithmic terms, if that's the question. Yes, so FAR R minus 2, FAR next minus 3, etc. And also another, okay, so and all another.
What is 0 in this middle term?
Okay, so because
0 and 2 the same terms?
No, okay, because we have changed the coordinates here. Maybe maybe the best option would be to forget about that line, because we would like to have good coordinate on the asymptotic. So x is just 1 over r, and we then transform it into standard Bondi coordinates. So this is maybe a relic from different things. So please, okay, forget about the middle equality here. So the asymptotic is just starts from r to the minus 2 here, and all other asymptotics are given by Maxwell equations here. Okay, so now we calculate all Hamiltonian charges and fluxes, and they behave very well, and also the flux are finite, so there is no problem in the case of Maxwell theory on the sitter at all. Okay, so the flux looks like equation 17, and so we can calculate it on each sphere of radius r, which cross the light cone and then pass with it into the infinity, and the limit is well behaved and exists without any problems. Okay, now I move to the linearized gravity, and here we use the machinery which stands behind our approach is based on the theory given by Kijowski and Tulchiev, and also independently by Walt and Zupas. And we start with the Lagrangian, and after all in the Legendre transformation and all other calculations are boundary terms are fixed, and our asymptotic conditions are modeled on the behavior of true full solution of the Einstein equation with positive cosmological constant, which is based on the Friedrich theorem. I will talk about it later. Okay, and yes, and we use here the standard Bondi conditions for the perturbed metric, and here all the background and the perturbation metric fulfills the Bondi gauge conditions. So this is the standard ones. This is comes from the condition for the two-dimensional determinant. Okay, and here we have what we have next. Okay, so this is all. So we consider the Lagrangian for a full theory, and here only we take the quadratic part and discarding a divergence in the Lagrangian only here. Okay, and the Lagrangian has the form given by 19. And this is used in the world Zupas formalis. And for a given Lagrangian, we also calculate the Hamiltonian current using Legendre transformation. And here, because we use in general our auxiliary fields, so here phi A is just H mu nu. Okay. Next, the canonical energy on a truncated light cone associated with a Hamiltonian current d over du is given by equation 22. And we have here volume term and also a boundary term given by equation 22. And as we will see, the boundary terms generates problems here, but it also is responsible for a so-called the standard Trautmann energy when we take the Minkowski limit. Okay, so next we are talk about the asymptotics. So we are basing here on the paper given by Friedrich, and the outcome is that we can find a dynamically consistent class of perturbation, which has an asymptotic equation, which is given by the equation 23. And we also do not have logarithmic terms here. The remaining components of the perturbation metric is given by the linearized Einstein equation. We use the version of the equation given by linearized version of the equation given by Winikur and Medler. And the analysis is quite complicated on the other terms, and everything is given in our paper in European Journal of Physics. The reference will be given at the end of the talk. Okay, and the boundary terms, it turns out, contains the leading divergent term, which is in the following, which has following structure. Okay, and the question is that what we can do with that. So the following questions begs for the answers. So the first one is that is there any chance to compensate the divergence by the volume integral? And if not, then is the question that the boundary term is needed at all in the definition of energy. And maybe we can obtain consistent solution by trying to get rid of that term which generates the divergent terms. And the answer for the second question I have already mentioned is that without the boundary term we cannot obtain a proper Trautmann Bondi flux in standard Minkowski spacetime, so we cannot neglect the boundary terms. The answer for the two questions needs to analyze the evolution equations. Okay, so we analyze one of that equation, and we see clearly that for answer C, if we set that HAB1 on one moment of time equal to 0, which evolves and become non-zero in the other moment of time. So we cannot set consistently that the leading term and HAB is 0, and it would evolve also in such way. Okay, so the answer for the third question is no. Okay, also the question is if we can compensate. Okay, and here we can clearly see that we cannot we cannot fix that HAB1 equal to 0 because it evolves. And the last question is, can we compensate the divergent boundary term by a volume term? And also here the analysis clearly shows that the contribution from a volume part is finite, so we cannot get rid of divergent term in such a way. So in such case, the only way is to propose the renormalized energy, but before that I would like to present the flux formula, and it turns out that the divergent terms evolves on its own. So it's a hope here that if we renormalize it, we have the finite energy and its flux, which evolves on its own. Okay, and we obtain the renormalized canonical energy by just removing the divergent term in canonical energy, and this is such energy have good quantities, and also we obtain good Trautmann-Bondi energy in the case in the limit when lambda goes to 0, and we can also do the same in the case of flux formula. Okay. Yes, so for lambda equal to 0, we recover the good Trautmann-Bondi massless formula. Okay, in the end, I will briefly talk about scalar field, and also in the case of scalar field, we have problems here. We consider in our convention the Lagrangian, the Lagrangian density, which looks like 34, and then we consider only a conformally covariant fields for which the equations of motions are preserved by the conformal transformation. So we consider massive field which a very specific mass which is proportional to the cosmological constant. Okay, and D here is the dimension of the space-time, and R is the Ricci scalar in that equation. Okay. Okay, analogically, we calculate the canonical energy momentum current, and here we use from the papers, Waze's papers, we can find the asymptotics of a scalar field which evolves from smooth initial data from some Cauchy surface have an asymptotic in the form 37. And for such asymptotics, we calculate energy, and also for scalar field, we have a divergent term. It was also confirmed recently in a paper given by Kostas Skenderis and collaborators. Okay. What is quite interesting here, if we calculate the angular momentum, which do not have, roughly speaking, the contribution from the cosmological constant exactly in the integrand, it turns out it's after integration by parts on the sphere, it gives the finite result. So at least in the asymptotics for big R, the angular momentum is finite here. Okay, and again, if we are interested in the flux of energy and angular momentum, and here again we have to assume that the Hamiltonian field is a Killing vector field, and also the equations of motion are fulfilled. So we consider only on-shell situation, and then the Lie derivative of Hamiltonian current is a purely boundary term here. Okay, and analyzing the energy flux, we have again the divergent term evolves on its own. So also in the case of scalar field, we can propose the normalization. Okay, maybe I can go to the summary. So all asymptotic conditions in each theories are I mean here the linearized gravity, so the asymptotic is modeled on the full solutions of the Einstein equations with positive cosmological constant. And in general, for scalar field and for linearized gravity, in Bondi gauge, the canonical charges are divergent, and the proposed renormalized energy and flux recover the classical Trondtmann-Bondi quantities. At the moment that we would like to calculate the inverse of the symplectic tooth form, and of course it's not so hard in the case of compacts on the functions with compact support, or if we neglect the boundary terms in other terms, but in other way. But if we would like to take into account the boundary terms and consider it, that is much more harder. Even in the scalar field, we have to analyze something which is called Fadeev construction. So if someone have any suggestions and ideas how to analyze the Poisson brackets in full generality, including boundary terms and on null surface, please let me know. So okay, the literature, the talk is mainly based of two papers given by two joint papers with Professor Chruściel and collaborators. So that paper in a European physical journal C contains all of the details. The paper in Physical Review. D is much more brief and contains only the most important facts. And at the moment, we also try to analyze the charges and the Poisson algebra, and we are in progress with that topic. Okay, so thank you. So I think I can stop here because this is all I have prepared for today, and I would like to hear your question. Okay, thank you very much.
Thank you very much. So there's time for questions. Who would like to ask? If nobody, I would like to ask. Can you show this slide with energy for this linearized gravity?
Sorry.
To see this term which you then remove, yeah.
Here, yes, but we haven't removed the whole boundary term, only some part of it. So.
Okay, so this is formula for canonical energy, and then you remove. Can you show the term you remove? Okay,
so in that version, it is the first
the first term you remove, and H1 is it corresponding to Bondi news somehow?
H1 corresponds to the
Bondi news would be differentiated with respect to you, but okay, but for differentiation, this is the term which leads to Bondi news.
It should correspond to the linearized Bondi news, yes.
So you say that you remove somehow square of this also shear tensor called sometimes,
yeah,
the integral of square of the shear,
yes, but in the next order you have that the first element in the next order is more or less responsible for a good Trautmann-Bondi mass loss formula. Yes, so this.
Why? Okay, for Trautmann there is no lambda, so there is no first term at all.
Yes, in the case of Minkowski there is no problem because that first term just vanished. So.
But I'm looking for some maybe to say physical reason is too much said, but to describe what really you remove, how to call the quantity you remove, not using indices, not using expansions. Probably it is hard to describe it in some asymptotic value of something.
Okay, so that I can say that the another terms have good evolution of its own. So even if we neglect that leading divergent term, the other terms evolves on its own. So in such sense, it's
but what is the my other question is the if you do this at level of energy, what is the corresponding change at level of Hamiltonian?
Sorry, so
if I understood well, you get this energy as a charge.
Yes, that energy is the integral from the Hamiltonian current on a truncated light cone. So yes.
So at the level of Hamiltonian, you remove what? The same term, or
on the level, because you have to integrate by parts to obtain the direct formula. Yes, because Hamiltonian gives only pure volume term. Yes, so it's some manipulations between the Hamiltonian and formula 22. Okay.
Yeah, but you understand my question. Is this renormalization of energy can be somehow translated to renormalization of Hamiltonian?
At the moment, I cannot tell you directly. So,
but you know, it would
if you understand the Hamiltonian as a functional, the answer is yes, because the energy is equal to the integral, to the volume integral from the Hamiltonian current, and then you can integrate by parts and neglect that divergent term.
Okay, you know, maybe this question is stupid, but if you can find any, say, renormalized Hamiltonian, then perhaps you can justify this renormalization, saying that nothing changes at the level of Hamiltonian and so on. Mm-hmm. Sorry, perhaps it is meaningless.
Yes, the best option would be to find the change on the level of boundary term in Lagrangian. Yes, because then
perhaps this, yeah, something. Yeah. So just you can look for some perhaps more other justification of this renormalization.
There is also I haven't mentioned, there is also a paper given by Professor Chruściel and Lukas Ifshitz, and they try to renormalize it in the general case, and they try to introduce something which is called the renormalized volume, but it's not well understood still, and that's the reason we are interested at the moment in linearized case.
Mm-hmm, mm-hmm. Okay, thank you very much.
Thank you very much.
Some other questions?
Can I ask a question?
Yes,
of course.
Yes. Can you tell me what this result means physically? So do I understand correctly that in the presence of positive cosmological constant, the weak gravitational wave, when approaches Scry, gets amplified to infinity? That's what you are saying?
Yes, in some reason, yes, we have divergent term, yes, but the question is,
so because it depends like linearly on lambda, so very small lambda makes this wave amplified, right?
Yes, this is still a mystery. I agree. This is we also try to analyze, maybe this is related with some gauge or something, but from the calculation you clearly see that there is a divergent term. Maybe it's a pure gauge or just shift in energy which is divergent, and it's do not give a exact physical contribution to the theory, but at the moment, so we have such term.
Pavel, you of course you remember that Scry now is
yes, I know that is space-like now. Yeah, I understand.
Yeah,
but that's my problem, because I think that even with Professor Demiański few weeks ago, we tried to calculate what's going on with the waves when approaching the Scry, and we were maybe we were wrong, but we saw that these waves are rather damped, and you are saying that they are just amplified. Interesting.
there is also the paper given by Professor Lewandowski and Maciek Kolanowski, and they calculate the energy between two null surfaces, if I remember correctly, and in such a case they also receive the finite result. So in such a case.
So might it be the artifact of linearization of this, that you are simply considering linearized equation? Maybe not. No,
because also in that full theory, so in the paper so that the Professor Chruściel and Lukas Ifshit consider they also have that divergent term, so it's rather not a case of wrong linearization or something.
See, I think that in full theory we don't have definition of energy for lambda. This is my opinion.
Yes, but I'm thinking about this from this point of view of this Penrose CCC model, because in this Penrose CCC model he considers these waves that are approaching the space-like scry, and then he says that since they are conformal, so they are passing to the next eon. So now you are telling me that actually when it approaches the scry, it approaches it with infinite energy, right? Interesting.
I don't know. There are two. You consider here linearized fields, and then you know what is Hamiltonian, what is flux, what is energy. Yeah? Mm-hmm. On the other hand, you have full theory where you don't know what should be called energy, and then you can try to you can define Bondi energy or Trautmann energy or something like this, which perhaps Mr. Smołka knows. You or Jacek Jezierski, you tried to prove that both energies agree in some conditions, at least.
Okay, that I would like to say, this is given in that long paper, that energy which is given on the screen is equal to the quadratization of Trautmann-Bondi mass up to some boundary terms in general. Mm-hmm. So that we can prove that, but there are still problems with that boundary terms here.
Mm-hmm. If there are so many groups working on the same just in Warsaw, interesting. Okay, thank you very much. Some other questions? No? So thank you again.
Thank you very much.
I thank all other people. Still this remark, if somebody wants to have